So, here in Chapter 13, we want to see how to find a general solution from a fundamental set of solutions. A fundamental set of solutions means that everything in the set is indeed a solution, which means we have to test it. We do all the derivatives and substitute them into the given differential equation and make sure that it is indeed true. And then we check for linear independence. Now, linear independence simply means that one of the functions is not some multiple of the other. And we'll see a convenient way of checking for that. So here we have the differential equation y double prime plus 4y equals 0. And we're given a set of two solutions, cosine 2x and sine 2x. So what we want to do is first off determine, are they indeed solutions to that differential equation? So we'll take the cosine of 2x, do its derivative and second derivative, substitute those in, and see is it true. Well, negative 4 cosine 2x plus 4 cosine 2x is indeed 0, so that is okay. We'll take the sine of 2x, do its derivative and second derivative, substitute that in, and see if it works. Now, since they both work, then they are both indeed solutions. Now, to check to see if they're linearly independent, we'll show you in just a moment a specific way of determining that. But what that means is basically that one is not some multiple of the other one. Now, sometimes we can kind of see whether or not this is true. We may have some sort of intuition into those functions. For example, for sine and cosine, I'm pretty sure that you can't take a sine function, multiply it by some constant, and get a cosine function, because as you know, sine and cosine are staggered from each other by a factor of 90 degrees. So I'm kind of thinking that there is not a way of multiplying one by a constant and getting the other one. So I'm thinking that they're not multiples of each other. Therefore, both conditions are met, and that's a fundamental set of solutions. However, we need a better way of determining linear independence. And that way is through something called a Wronskian. Now, the Wronskian is a determinant formed by each function in the set and its associated derivatives. Now, this is a determinant. If you've never experienced determinants before, a determinant is a square matrix that has a particular evaluation. I'll show you how to evaluate some determinants shortly. However, let's see for this particular example how we would write a Wronskian. Now, what we do is evaluate the Wronskian and determine if it's equal to 0. If it's not 0, then it's linearly independent. So we want Wronskians that are not 0. If it's 0, then it doesn't work. It's not independent. So, taking the cosine of 2x and sine of 2x, doing their derivatives, and writing that into a determinant. Now, the determinant, since we have two solutions, cosine 2x, sine 2x is our two functions. They're written across the top. Their associated derivatives are written just below them. Now, if we had 3, we would have a 3 by 3 determinant, and we'd have to do a second derivative. I'll show you one of those in just a moment. To evaluate a 2 by 2 determinant, you multiply diagonally, beginning with the upper left and the lower right, and multiply the other two diagonals and then subtract. Multiply, multiply, subtract is the order for evaluating a 2 by 2 determinant. Or you could type it into your calculator, as I'll show you later. So anyway, we evaluate the determinant. We come up with a 2. Now, since that is not 0, then we know that they are linearly independent. I kind of suspected they were, but now we know for certain that they are linearly independent. Now here's the Wronskian with 3 functions. Since we have 3 functions, we will need a first and second derivative. So we'll go ahead and do those for each of the 3 functions. And then our determinant will look like this. We'll have the function y1 along with its derivatives. We'll have the function y2 along with its derivatives. And then we'll have the function y3 along with its derivatives, first and second in that order. So, to evaluate this determinant by hand would require a process known as expansion by cofactors. I can't go through the entire process in this short video, so you may want to go investigate that if you intend to be evaluating these by hand. However, we can expand this determinant about this first column by writing down the 1, 0, and 0, and then eliminate the row and the column where the 1 is, and write down the remaining 2 by 2 determinant. So this would be a 1 times negative 2 sine 2x, 2 sine x cosine x, negative 4 cosine 2x, and then 2 cosine squared plus 2 sine squared. And here we would do the same thing, only I'm not going to take the time to write it all down, because as you can see, the determinant we come up with here when multiplied by 0 is just going to be 0. Likewise, for this other one, the determinant would still be multiplied by 0. Now, this is what we end up with, 2 by 2 determinant, which we do like we did earlier, multiply diagonally and subtract. Now, I won't finish that out. The point being, it's quite a lengthy process to do a 3 by 3 determinant by hand. However, on the TI graphing calculator, you can enter the determinant, 3 by 3 determinant, and you can do DET, and it evaluates the determinant. Now, as you can see, this evaluates to a function, not to a specific number. And I'm simply going to evaluate this for some values of x. I've chosen 3 values, x equals 0, x equals pi, and x equals pi over 2. And notice all of those give an answer of 0, which means these are not linearly independent. So here are the steps that we're going to perform now that we know how to check for linear independence. So here's a third order equation with its initial conditions and 3 solutions. We need to check to see if they are indeed linearly independent and if they are indeed solutions. So we'll use the Wronskian to check for linear independence. Here's the derivatives that we need for the Wronskian. We'll put those into the proper order and evaluate the determinant using our TI graphing calculator. Notice the determinant of that comes out to be just the number 8, which means it is always not equal to 0, which means they are always linearly independent. And next we'll check to see if they are actually solutions to begin with. So we'll take the y1, substitute in, well, in order to substitute, we're going to need the third derivative of that. So we'll go ahead and compute the third derivative and then plug that in. Well, we get 0 equals 0, which tells us that it is indeed a solution. Likewise, to check to see if y2 is a solution, we need its third derivative. We plug that in, simplify, and that is indeed equal also. And then we check the third function to see if it is indeed a solution. And notice that comes out to be 0 equals 0. So they are all solutions. So now we want to write a function that contains all three of these along with the associated constants. So this would be 1 times c1 plus cosine 2x times c2 plus sine 2x times c3. We have to have the three constants since we have a third order differential equation. Here is what we do. We want to begin with the condition y0 equals 3, substitute those values, simplify, and we'll take that equation later and solve it for the C1, C2, and C3. We do the derivative, substitute the next condition, and simplify. And we do the next derivative using the third condition. We'll substitute and simplify. Now we need to solve those three equations simultaneously. Sometimes that may involve more algebra than what we're about to do. We can take the bottom equation, divide both sides by -4, and get C2. We can take the middle equation, 2c3 equals 8, divide by 2 and get c3. We can take the top equation, c1 plus c2 equals 3, use the c2 that we just found, and get c1. So then we rewrite our function with the constants that we just found.